Hello everyone, my name is Jesse from Curtin University, and today I'm going to be showing off our SAVER version 2 prototype. So SAVER is the simple available ventilator for emergency response. We started working on this project about a month and a half ago, and within a week we turned around our version 1 proof of concept. And using what we learned from that, as well as consultation from medical professionals, researchers, engineers, and all of that we've come up with our version 2 prototype here. So this is a vast improvement over version 1. And we'll be developing this further into version 3 to overcome some limitations that this machine has, which we'll get into in a minute. Although the COVID pandemic, coronavirus is looking like it's nearing the end, we're designing this to account for a second wave, a future pandemic like this, or just to increase our local ability to manufacture ventilators like this, given that we've shown they're in quite short supply. In early April, the Therapeutics Goods Association of Australia, or the TGA, released this document outlining 34 mandatory and 13 optional criteria for building a ventilator like this to respond to COVID-19. The goal of these kind of ventilators is to be locally manufactured and rapidly producible. What we've done is that we've taken version 1 and version 2 of our SAVER prototype, so version 2 is what you see here, version 1 is our earlier one, and we've evaluated against this criteria. Version 1 met 9 of these 47 total criteria, and this one meets 23. Now, we're still a bit behind, and we want to resolve most of those by our next iteration, version 3. But the main thing holding us up is the supply chain. So because a lot of businesses are currently closed down due to COVID restrictions, it's very hard to get our hands on parts which are suitable for a ventilator, especially in this domain, where parts have to be usable in very low pressures, but at very high flow rates. Furthermore, they have to be biologically safe. So that's one of our main restrictions. The other one is actually safety. Because ventilators like this can mix oxygen, that requires oxygen gas, which is very flammable, and we can't currently use it in the lab. So that's something that we're trying to resolve before version 3 so that we can test the oxygen and air gas mixture. The structure's in there, but we just have no way to test it yet because of safety restrictions. Okay, so as you can see here, we've got our SAVER v2 prototype running. This is in pressure-controlled ventilation mode, using this lovely, pretty blue glove as our analog for a human lung. And what you can see here is really what sets this apart from a lot of the designs that you've probably seen before of rapidly manufactured ventilators, and that's the interface. So we've taken great care to model this after existing medical equipment and ventilators in order to make sure that medical professionals using this need the least amount of excess training possible. Now here we're running inside a pressure-controlled ventilation, which is controlling the patient pressure based on some set point given to the user, and we can edit that set point here. So we can come into here, we can drag this around, we can manually update it. You can do it with either a touchscreen, a mouse and a keyboard, or whatever you happen to have available. This will run on any laptop, anything that can run Linux, Windows, Mac, anything. So we can go ahead and hit apply there. It's going to try and apply that pressure here. Our set point currently is 30, and you can see that we're getting pretty close to that, around 28 to 31. And what's going on here is we're seeing this pressure control waveform. Now, if you've seen these waveforms before, if you're a medical professional or happen to know what these should look like, you'll notice that this isn't quite correct, and you would be right in saying that. The reason being is because we're lacking a bit of control here. We need a few more sensors and actuators which are being held up in the supply chain that we can't get access to as quickly as we need to. So we're testing what we can on the version 2 prototype, and it's doing pretty well so far for the parts we have. And we're going to refine this for version 3. So now that we're in here, I can simulate a overpressure event. So a patient's being overventilated or something has gone wrong. I can come into here on the inhale cycle, squeeze the balloon a bit so that the pressure increases. You can see we've got a spike there. I can go ahead and pause this UI. I can go in, I can take a look at the problem. I can go, oh, okay, that's at this level. We've gone over there. It's flashing bright red to say that there's been an alarm, showing you where the alarm limits are. Usually this would make a sound as well, but to be honest, it's quite annoying, so we've turned it off. And once we're satisfied that we can overcome that, we can go ahead and resume, clear the alarms, and we're good to go. So that's pressure-controlled ventilation, and that's working a pretty good treat. We can adjust all kinds of things here, including a crucial element called peak end expiratory pressure, or PEEP. What we've got down here is, you'll notice that the pressure never drops to 0. This is very important because if it drops to 0, you have increased risk of causing some kind of trauma to the lung. So we need to prevent that. We need to keep at least some pressure in there, which is why this glove isn't fully deflating. And you can see we're achieving that here. So we're never going below that red line. And so we're keeping the correct pressure that we need to. And this is true for all modes that this operates in. So now that we've seen that, we can go ahead and take a look at some of the other modes of ventilation as well. For example, volume-controlled ventilation. Now remember, we're missing a few sensors and actuators, so this isn't going to look quite right, but it's getting pretty close. Instead, we're controlling based off this volume graph here, which is not the waveform that we're after, but it's what we've got. And the pressure is a result of that. So we're trying to reach around 220 milliliters. At the moment, we're peaking around 220 to 250, just based off of the gear that we have here. We can edit a whole bunch of other stuff here as well, like the IE ratio, how long to breathe in versus breathe out in a given cycle. The respiratory rate, so how many breaths per minute, as well as oxygen concentration. But for safety reasons, we don't have the flammable oxygen gas hooked up to this. But you can adjust this all the way from what's just in the air to 100 to wherever you need. This is supplemental plus air. So that's volume-controlled ventilation and pressure-controlled ventilation. These are both pretty standard. You've probably seen these on existing prototypes before. But today we'd like to demonstrate one in particular, and that is spontaneous mode. Spontaneous mode is a kind of ventilation where it syncs up with the patient's effort. So the patient is giving the trigger to do a breath in or out.
Here we can see spontaneous mode running inside of simulation. So with a simulated lung and a simulated ventilator, since it's quite hard to test without an actual breathing person. And what we can see is a typical respiratory cycle, but instead of being triggered based just off time, it's triggered based off patient effort. So in cases where the patient can breathe a little, but not quite all on their own, this mode is really useful since it allows the patient to trigger the next breath on their own, and the ventilator can provide pressure support. So what we can see are small dips on the inhale of each cycle. That's when the patient is trying to breathe in, since the volume of their lungs is increasing to draw in more air, the pressure decreases, which triggers our inhale cycle. And then with that small spike in pressure, when the patient's attempting to breathe out, we fall back down to the PEEP value and wait for the next inhale. Now, if this doesn't happen within a certain period of time, it will fall back into a mandatory ventilation mode to ensure that the patient keeps breathing. When we've talked to medical professionals, this is the most demanded mode that we've got, presumably because it is more suitable for long-term ventilation, as well as weaning patients off of ventilation and providing the least amount of risk since it's not mandatory. This isn't something that we've seen on existing rapidly manufactured ventilators, so we're very excited to present this mode.
And by using all of these modes, pressure-controlled, volume-controlled, and spontaneous, we can account for a variety of situations, give patients the best care that they need, depending on the doctor's expertise, what they want to set, what the medical professional wants to set these parameters as. And this ventilator will be able to keep up with that and give them the information that they need, whether it's from the end of the bed, which is why all the text is quite big, or from a nurse's station. You can actually view this on multiple machines at once, from a nurse's station, wherever you like to go, and make sure that the patients are getting the care that they need and that they're responding to that care properly by looking at these values here, instead of trying to twist knobs on a physical machine. Now, the big question is always reliability, and that's something which we take very, very heavily. You might be looking at this and going, wow, this can run on any laptop, any computer, but my computer crashes all the time. Isn't that bad? We don't want a ventilator to crash. Well, the good thing is I can actually completely unplug this from a computer and it keeps running on its own. So this is no longer, there's nothing plugged into my computer anymore, there's no Wi-Fi. This has stopped responding, so this is of course going to alarm saying, in this case the controller's offline, I can't find the ventilator. The ventilator itself would also alarm, but again we've disabled it because it's quite annoying. But you can see it's functioning just fine on its own. And then we can come in, we can fix that issue, plug it back in and be good to go again. Okay, sorry, one thing I forgot to mention. This machine isn't actually running off of any kind of central gas network. It does have some of its own air tanks, but at the moment it's actually running off of this compressor down here, which you can hear flick on. Very fortunate timing. So if you're not in a hospital, if it's a big disaster situation and central gas is not available, you could hook it up to a compressor and an oxygen tank, and this machine will be able to run on its own. So there's no need to tether it to this. All it needs is power and some source of air, be it compressor, and some source of oxygen. A cylinder, central gas, oxygen concentrator, either one. Thank you for tuning in, and we're very excited to continue this further.